Dry-type transformers generate electromagnetic fields. These fields can interfere with electronic devices. This interference is known as electromagnetic interference, or EMI. Symptoms of EMI can include computer crashes or freezes, data loss or corruption, network connectivity issues, and display problems. Several solutions can be implemented to mitigate EMI. Firstly, increasing the distance between the transformers and the personal computers reduces the strength of the EMI. Secondly, install ferrite cores on cables. Ferrite cores fit over cables to absorb EMI. Thirdly, use shielded cables. Shielded cables have a metallic coating that prevents EMI from entering or leaving the cable. Fourthly, enclose the transformers in a Faraday cage. A Faraday cage is a conductive enclosure that blocks electromagnetic fields. Dry-type transformers dissipate heat. This heat can raise the temperature in the computer lab. Excessive heat can damage computers and other electronic devices. To deal with heat, firstly provide adequate ventilation. Install fans or air conditioners to circulate air and cool the computer lab. Secondly, insulate the electrical room. Insulating the walls and ceiling of the electrical room can reduce the transfer of heat to the computer lab. Wall materials are another consideration. The materials used for the walls between the electrical room and computer lab can affect the level of EMI shielding. Metal walls provide better shielding than drywall. Transformer size also matters. The size of the transformers will influence the strength of the EMI generated. It's important to gather detailed information about the specific computer problems being experienced, including the make and model of the computers, distance to the transformers, and any troubleshooting steps that have been taken. Several products are available for EMI shielding. Electromagnetic shielding paint can be applied to walls, ceilings, and equipment to create a conductive surface that reflects EMI. EMI shielding fabrics can be used to create curtains or other barriers to block EMI. Prefabricated EMI shielding enclosures can be installed to surround the transformers and contain the EMI. Consider the location and specifics of the computer issues to determine the best course of action. Remember to carefully assess the environment and type of equipment you are working with. Consider all safety precautions and follow proper procedures when making changes to electrical installations. Shielding is grounded for safety reasons to provide a path for stray currents to flow safely to ground. If shielding is not grounded, it can become energized and pose an electrical shock hazard. Grounding also helps to reduce noise and interference in electrical systems. A proper ground connection ensures that the shielding is at the same electrical potential as the surrounding environment. This prevents voltage differences that can cause current to flow and create noise. Proper grounding is essential for ensuring the safety and effectiveness of shielding in electrical systems. Grounding the shield drains away any capacitively coupled current, preventing it from being induced on the inner conductors. Shielding effectiveness measures how well a shield attenuates electromagnetic fields. It is typically expressed in decibels, which represents the ratio of the field strength without shielding to the field strength with shielding. A higher decibel value indicates better shielding effectiveness. Shielding effectiveness depends on several factors, including the material, thickness, and construction of the shield, as well as the frequency and polarization of the electromagnetic field. Different shielding materials have different shielding effectiveness at different frequencies. Copper and aluminum are commonly used shielding materials due to their high conductivity and good shielding effectiveness over a wide range of frequencies. The thickness of the shield also affects its shielding effectiveness. Thicker shields generally provide better shielding than thinner shields. The construction of the shield, such as whether it is solid or mesh, can also affect its shielding effectiveness. Solid shields typically provide better shielding than mesh shields. The frequency and polarization of the electromagnetic field also affect shielding effectiveness. Shields are generally more effective at attenuating high-frequency fields than low-frequency fields. The effectiveness of shielding also depends on the polarization of the electromagnetic field. Understanding the factors that affect shielding effectiveness is essential for selecting the appropriate shielding material and construction for a particular application. The specific grounding method will depend on the application and the type of equipment being shielded. The grounding conductor should be as short and direct as possible to minimize impedance. The grounding conductor should be connected to a low impedance ground point. Shielding can be grounded at one end or at both ends. Grounding at one end is generally preferred for low-frequency applications, while grounding at both ends is preferred for high-frequency applications. The single-point grounding of a shield is designed to prevent ground loops. Ground loops occur when multiple ground connections create a loop in the grounding system, which can induce currents and noise in the loop. Grounding the shield at only one point avoids creating such a loop. This is particularly important in sensitive electronic circuits where even small amounts of noise can cause problems. The shield acts as a barrier to prevent external electromagnetic interference from reaching the signal conductors inside the cable. By grounding the shield at one end, any induced noise currents are directed to ground without flowing through the signal conductors. This helps to maintain the integrity of the signal and prevent it from being corrupted by external interference. Grounding both ends of a shield can create a ground loop, which can introduce noise and interference into the system. Ground loops occur when there are multiple paths to ground, creating a loop in the ground system. This loop can act as an antenna, picking up electromagnetic interference from the environment and injecting it into the signal conductors. The impedance of the shield affects its shielding effectiveness. Lower impedance shields generally provide better shielding than higher impedance shields. The impedance of the shield depends on its material, thickness, and construction, as well as the frequency of the electromagnetic field. Proper termination of the shield is essential for maintaining its shielding effectiveness. Improper termination can create gaps or discontinuities in the shield, which can allow electromagnetic fields to leak through. The shield should be terminated to a low impedance ground point to provide a path for induced currents to flow safely to ground. Filters are designed to block or attenuate unwanted frequencies while allowing desired frequencies to pass through. They are commonly used in electronic circuits to remove noise, reduce interference, or shape the frequency response of a signal. Filters can be classified into different types based on their frequency response characteristics. Low-pass filters allow low frequencies to pass through while attenuating high frequencies. High-pass filters allow high frequencies to pass through while attenuating low frequencies. Band-pass filters allow a specific range of frequencies to pass through while attenuating frequencies outside that range. Band-stop filters, also known as notch filters, attenuate a specific range of frequencies while allowing frequencies outside that range to pass through. Filters can be implemented using different types of components such as resistors, capacitors, and inductors. Choice of components and the filter topology will depend on the desired frequency response and the specific application requirements. Filters are widely used in various electronic systems, including audio equipment, communication systems, and power supplies. They play a crucial role in improving signal quality, reducing noise, and ensuring the proper functioning of electronic devices. Faraday cages are enclosures made of conductive material that are designed to block electromagnetic fields. They work by creating a conductive barrier that redirects electromagnetic fields around the inside of the cage. The conductive material of the Faraday cage provides a path for electric fields to flow, preventing them from penetrating the interior of the cage. When an external electromagnetic field encounters the Faraday cage, it induces currents in the conductive material. These currents create an opposing electromagnetic field that cancels out the original field inside the cage. The effectiveness of a Faraday cage depends on several factors, including the conductivity of the material, the size and shape of the cage, and the frequency of the electromagnetic field. Faraday cages are commonly used to protect sensitive electronic equipment from electromagnetic interference such as radio waves, microwaves, and electromagnetic pulses. They are also used in scientific research to create shielded environments for experiments. In addition to electronic equipment, Faraday cages can also be used to protect people from electromagnetic fields. For example, they are used in MRI rooms to prevent external radio frequency signals from interfering with the imaging process. The shielding effectiveness of a Faraday cage is typically measured in decibels. A higher decibel value indicates better shielding performance. The shielding effectiveness of a Faraday cage can be affected by openings or gaps in the conductive material. Even small openings can allow electromagnetic fields to penetrate the cage. To maintain the shielding effectiveness of a Faraday cage, it is important to ensure that all seams and joints are properly sealed. Conductive gaskets or tape can be used to seal openings and prevent electromagnetic leakage. The thickness of the conductive material also affects the shielding effectiveness of a Faraday cage. Thicker materials generally provide better shielding than thinner materials. The choice of material for a Faraday cage depends on the specific application requirements. Copper, aluminum, and steel are commonly used materials due to their high conductivity and good shielding properties. The size and shape of a Faraday cage can also affect its shielding effectiveness. In general, larger cages provide better shielding than smaller cages. The shape of the cage can also affect the distribution of electromagnetic fields inside the cage. Faraday cages are used in a variety of applications, including telecommunications, aerospace, and medical imaging. They are an essential tool for protecting sensitive electronic equipment and ensuring the accuracy of scientific measurements. Proper installation and maintenance are crucial for ensuring the long-term performance of a Faraday cage. Regular inspections should be performed to check for any damage or deterioration of the conductive material. Any openings or gaps should be promptly sealed to maintain the shielding effectiveness of the cage. The effectiveness of EMI shielding depends on frequency. Different materials and techniques are effective at different frequencies. Understanding the frequency range of the EMI is crucial for selecting the appropriate shielding method. Low-frequency EMI is typically caused by power lines, transformers, and other electrical equipment. High-frequency EMI is typically caused by radio transmitters, cell phones, and other wireless devices. The type of EMI source can also affect the choice of shielding method. For example, magnetic fields are best shielded with ferromagnetic materials, while electric fields are best shielded with conductive materials. In some cases, a combination of different shielding methods may be required to effectively mitigate EMI. Conductive materials, such as copper and aluminum, are effective at shielding against electric fields. They work by creating a conductive path for the electric field to flow, preventing it from penetrating the shielded area. Ferromagnetic materials, such as steel and iron, are effective at shielding against magnetic fields. They work by providing a low-reluctance path for the magnetic field to flow, diverting it away from the shielded area. Absorptive materials, such as ferrite and rubber, are effective at absorbing electromagnetic energy. They work by converting the electromagnetic energy into heat, reducing the amount of energy that is transmitted through the shielded area. The choice of shielding material will depend on the type of EMI source, the frequency range of the EMI, and the desired level of shielding effectiveness. Shielding effectiveness is typically measured in decibels, which represents the ratio of the electromagnetic field strength without shielding to the field strength with shielding. A higher decibel value indicates better shielding effectiveness. The shielding effectiveness required for a particular application will depend on the sensitivity of the electronic equipment being protected and the level of EMI present in the environment. In some cases, it may be necessary to perform EMI testing to determine the level of EMI present and the effectiveness of the shielding. EMI testing involves measuring the electromagnetic field strength in the shielded area and comparing it to the field strength outside the shielded area. The results of EMI testing can be used to evaluate the effectiveness of the shielding and to identify any areas where the shielding needs to be improved. In addition to shielding materials, other techniques can be used to mitigate EMI, such as filtering, grounding, and cable management. Filtering involves using filters to block or attenuate unwanted frequencies. Grounding involves providing a low impedance path for currents to flow to ground, reducing the amount of noise and interference in the system. Cable management involves organizing and routing cables to minimize the amount of EMI they radiate. A well-designed and properly implemented EMI mitigation strategy can significantly improve the performance and reliability of electronic equipment. When selecting EMI shielding products, it is important to consider the specific requirements of the application and the performance characteristics of the product. Consider the frequency range of the EMI, the level of shielding effectiveness required, and the environmental conditions in which the products will be used. It is also important to choose products that are compatible with the other components in the system and that meet any applicable regulatory requirements. Electromagnetic compatibility, or EMC, is the ability of electronic equipment to function properly in its intended electromagnetic environment without causing interference to other equipment. EMC is an important consideration in the design and operation of electronic equipment, as it can affect the performance, reliability, and safety of the equipment. EMC is typically achieved through a combination of design techniques, shielding methods, and filtering techniques. These techniques are used to minimize the amount of EMI generated by the equipment and to protect the equipment from external EMI sources. EMC testing is used to verify that electronic equipment meets applicable EMC standards and regulations. EMC testing involves measuring the amount of EMI generated by the equipment and the susceptibility of the equipment to external EMI sources. The results of EMC testing can be used to identify any areas where the equipment needs to be improved to meet EMC requirements. EMC standards and regulations vary from country to country. In the United States, the Federal Communications Commission, or FCC, regulates EMC for electronic equipment. In Europe, the European Union, or EU, regulates EMC through the EMC Directive. Compliance with EMC standards and regulations is essential for electronic equipment to be sold and operated in many countries. Non-compliance with EMC standards and regulations can result in fines, product recalls, and other penalties. A comprehensive EMC program should include design guidelines, shielding methods, filtering techniques, grounding practices, and cable management practices. The EMC program should be documented and should be followed throughout the design, manufacturing, and testing processes. Regular EMC audits should be conducted to ensure that the EMC program is being followed and that the equipment continues to meet EMC requirements. A well-designed and properly implemented EMC program can significantly reduce the risk of EMI problems and ensure that electronic equipment functions properly in its intended electromagnetic environment. The size and shape of the transformer can also affect the level of EMI generated. Larger transformers tend to generate more EMI than smaller transformers. Transformers with open cores tend to generate more EMI than transformers with closed cores. The location of the transformer in the electrical room can also affect the level of EMI in the computer lab. Transformers should be located as far away from sensitive electronic equipment as possible. The orientation of the transformer can also affect the level of EMI in the computer lab. Transformers should be oriented so that their magnetic fields are not directed towards sensitive electronic equipment. The type of transformer can also affect the level of EMI generated. Dry-type transformers tend to generate less EMI than liquid-filled transformers. Transformers with electrostatic shields tend to generate less EMI than transformers without electrostatic shields. The installation of the transformer can also affect the level of EMI in the computer lab. Transformers should be properly grounded to reduce the amount of EMI they radiate. Transformers should be installed in accordance with all applicable electrical codes and standards. Regular maintenance of the transformer can also help to reduce the level of EMI generated. Transformers should be inspected regularly for any signs of damage or deterioration. Transformers should be cleaned regularly to remove any dust or debris that may be contributing to EMI. A well-maintained transformer will generate less EMI than a poorly maintained transformer. Addressing the symptoms of EMI involves identifying the specific symptoms that are being experienced and then taking steps to mitigate the symptoms. For example, if the computers are crashing or freezing, the first step is to determine whether the crashes or freezes are caused by EMI. This can be done by monitoring the computers for EMI and by testing the computers in a shielded environment. If the crashes or freezes are caused by EMI, the next step is to identify the source of the EMI. This can be done by using an EMI meter to measure the electromagnetic field strength in the computer lab. Once the source of the EMI has been identified, the next step is to take steps to mitigate the EMI. This may involve implementing one or more of the shielding methods, filtering techniques, grounding practices, and cable management practices described above. The effectiveness of the EMI mitigation measures should be verified by monitoring the computers for EMI and by testing the computers in a shielded environment. If the EMI mitigation measures are not effective, additional measures may need to be taken. It is important to know that EMI problems can be complex and may require a combination of different mitigation measures to be effectively addressed. It is also important to consult with qualified professionals to ensure that the EMI mitigation measures are properly implemented and that they meet all applicable safety and regulatory requirements. Heat is the flow of energy from a hot object to a cold object. Heat can be transferred by conduction, convection, or radiation. Conduction is the transfer of heat through a material. Convection is the transfer of heat by the movement of a fluid. Radiation is the transfer of heat by electromagnetic waves. Dry-type transformers generate heat as a result of the energy losses associated with the magnetization and demagnetization of the core material, as well as the resistance of the windings to current flow. The heat generated by a dry-type transformer can raise the temperature in the computer lab. Excessive heat can damage computers and other electronic devices. To mitigate heat, firstly, provide adequate ventilation. Install fans or air conditioners to circulate air and cool the computer lab. Secondly, insulate the electrical room. Insulating the walls and ceiling of the electrical room can reduce the transfer of heat to the computer lab. The amount of ventilation required will depend on the size of the transformer, the load on the transformer, and the ambient temperature in the computer lab. The insulation should be installed in accordance with all applicable building codes and standards. Regular maintenance of the ventilation and insulation systems is essential for ensuring that they are functioning properly. The ventilation system should be inspected regularly for any signs of damage or deterioration. The insulation should be inspected regularly for any signs of damage or degradation. A well-maintained ventilation and insulation system will help to keep the computer lab cool and prevent damage to computers and other electronic devices.